Hello, everyone. Hope you're all doing great. Welcome back to this lecture series on failure theories. Today's topic is magic matrix. I'm just using the word magic matrix, but conventionally the topic is eigenvalues and eigenvectors. So if you're looking for the word magic matrix in textbook, you're not going to find it, but it's a very cool concept, so I would love to use the word magic matrix. But nothing magical about it. Everything is going to be mathematical and logical, but the concept is really, really cool. So the prerequisite to today's session, you should know matrix multiplication in order for you to appreciate the concept of eigenvalues and eigenvectors. You should know the matrix multiplication, and you should know what is a vector. And of course, in today's session, we are not going to talk about the physical scenario. So once we are done with the mathematics, once we wrap our mind around the mathematics, then we will integrate this mathematics with the physical scenario, so it makes perfect sense. So to begin with, before we answer this question, what is a magic matrix? We have to ask this question: what happens when a matrix hits a vector? So that's the question that we are going to answer now. So first, just imagine that we have got a vector like the one that you see here. There you could see the vector. It has a magnitude. It is given by the length of the vector. Of course, it also has a direction. That is the arrow mark that you see. That's the direction of the vector. Of course, the length of the vector along the horizontal component of the vector is 1 unit, and the vertical component of the vector is 1 unit. So you can just take any vector, but I'm just taking this vector for example. It is easy to work with. So horizontal component, that you could see that it has got a length of 1 unit, and the vertical component, it has got a length of 1 unit. So we can simply write this vector v vector as 1i vector plus 1j vector. So the 1i representing the horizontal component and the 1j representing the vertical component. But we can also represent this vector in the form of a matrix. Here is the column matrix. So there you could see that we are representing the vector in the form of a column matrix 1, 1. Whereas the first entry in this matrix represents the horizontal component, and the second entry in the matrix represents the vertical component. Now, the question that we asked: what happens when a matrix hits this particular vector? So here we go. Here is a matrix. So let me zoom this up a little bit. So we are going to hit this matrix with this vector. The converse is equally true. We are going to hit this vector with this matrix. So the matrix, it's a 2-row, 2-column matrix, 2-by-2 matrix. And the vector, it has 2 rows and 1 column. So when you're hitting the 2-by-2 matrix with your 2-bar 1-column vector, you are going to get a 2-bar 1-column vector back, right? So let us see what happens when you hit this vector with this matrix. So here we go. So when you're hitting this matrix 3, 2, 4, 0 with this vector 1, 1, then it completely transforms the vector. You see the 1, 1 becomes 6, 4. So that's the matrix multiplication. I'm assuming that you are all familiar with the matrix multiplication. So the 1, 1 vector now becomes 6, 4 vector, which means that if you just have to plot it again as a graph in the graphical representation, there you could see initially we had this vector, this red arrow vector, where the horizontal component is 1 and the vertical component is 1. Now if you look at this particular vector, it is completely transformed. It is completely transformed into a new vector. There you could see the blue line there. So that represents the completely transformed vector. So the answer to this question: what happens when a matrix is going to hit a vector? The answer to this question is: when a matrix is going to hit a vector, it completely transforms the vector. Now, just to make sure that we remember this concept, so here we go. So when a matrix is going to hit a vector, it's going to completely transform the vector just like this. Okay, good one. I hope you are not deviating from the topic, but the point that I wanted to emphasize is that you see that there is a complete transformation. Previously, it was one person, and after that, it's a completely different person. Just like that, a vector becomes a completely different vector. So that is what happens when a matrix hits a vector. But that is not always the case. There is a particular matrix. We call that as the magic matrix. When that particular matrix, the magic matrix, there you could see that 2, 1, 1, 2, when this matrix is going to hit this vector 1, 1, then it's not completely transforming the vector. That you could see that it is 1, 1 becomes 3, 3. So there is not going to be a complete transformation, but there is going to be a magnification, because 1, 1 becomes 3, 3, or 1, 1 is becoming 6, 6, something like that. So it's not completely transforming the vector, but what it is instead doing is it is actually magnifying the vector. So that happens when that vector 1, 1 is hit by a magic matrix. So now we can say that every vector should be having a particular magic matrix. When that magic matrix hits that vector, instead of completely transforming the vector, it just elongates the vector or compresses the vector. It just magnifies the vector or it diminishes the vector. So such a matrix is what I'm calling that as a magic matrix. Okay? So we will see that here what happens is you could see that we started with the red arrow, that is the 1, 1 vector. Horizontal component is 1, vertical component is 1. Now you see that when it is hit with this magic matrix, what happens is this vector 1, 1 becomes 3, 3. So there is no complete transformation. So you could see that it's just going along its line of action. There is an elongation along its line of action. Okay, again, just to make sure that we remember this concept, here we go.
गुस्से में ही रहता हूँ।
Okay, again, I hope that we are not deviating from the topic. So you could just watch these videos at the privacy of your room at your leisure, but not compromising on our studies. Yes. So that is, you see that there is not going to be a complete transformation. There is a magnification, right? Just like a Hulk, there is a magnification. Okay. So that is what is called as the magic matrix. Okay. So we will see that here. You could see that it just magnifies by an amount 3. So this magnification factor, we will say that it is lambda. So these magnification factors are called as the Eigen values. Hope that now it is clear. I hope to some extent we have demystified what is an Eigen value. The magnification factor, that is what is called as the Eigen values. Okay. So now we will assume that for a given matrix, we will assume that we don't know what is the eigenvalue. Because initially, if you're provided with a matrix, how will you know what is the eigenvalue? How will you know what is the magnification factor? You will not know, right? So we will assume, in our case, we know that it is 3, but originally, when we when we want to start with a given matrix, we will not know what is the eigenvalue. So we will assume that we don't know what is the eigenvalue, the magnification factor. So we will call that as lambda. And we will also do not know what the vectors are. So those vectors are called as Eigen vectors. So this 1, 1 vector, initially we don't know whether it is a 1, 1 vector or whether it is a 2, 3 vector. So we don't know. So we will say that it is alpha, beta. So the above equation, you see that it just becomes this particular equation that you can see that here, it should become this equation that you see here should become this equation, because the 1 1 vector now it is called as alpha beta, because we don't know, right? We don't know. And the magnification factor, we don't know. For a given matrix, we cannot just tell. We have to do the mathematics. So how will we find, how is that we are going to find what is the magnification factor, which means eigenvalues, and what is the corresponding vector, eigenvectors? How is that we are going to find out? So we are going to see that procedure just now. So there you could see it is 2 1 1 2. Alpha beta is equal to lambda, which is the magnification factor, into alpha beta. Okay. Now what I'm going to do is I'm just going to multiply here in this region. I'm just going to multiply by the identity matrix. Now, if I just multiply by identity matrix, it's just like multiplying by 1 to a digit, analogous to multiplying 1 to a digit. When you multiply by identity matrix, you are not actually going to do any damage to the equation, right? So I'm just multiplying by this identity matrix that you see here, 1 0 0 1. So that is the identity matrix that I'm multiplying with. Now what I'm going to do is I'm just going to throw the right hand side term. I'm going to bring it to the left hand side. So the right hand part becomes 0. So that you can see that in this step I have brought the right hand side to the left hand side. So the right hand side is equal to 0. And again, you could see that I'm bringing the alpha beta terms common. So I have taken the alpha beta here. So there you can see this alpha beta is taken common, and the right hand side is equal to 0. Now this is of the form A matrix, which we call this matrix as the A matrix, and we will call this as the identity matrix. That's very well. So it is of the form A matrix minus lambda I into this eigenvector is equal to 0. We know that the eigenvectors, they are not going to be 0. So if A matrix into B matrix, in short, if the matrix is of the form U matrix into V matrix, if it is equal to 0, then determinant of U should be equal to 0 if V vector is not equal to 0. So determinant of U should be equal to 0 by the rule of mathematics. So we can say that the determinant of A minus lambda I should be equal to 0. So we are just going to take the determinant. So determinant of 2 minus lambda. So there you can see 1 minus 0 is 1. And here 1 minus 0, again it is 1. And 2 minus lambda. So that determinant should be equal to 0. So once you take the determinant, you end up with a quadratic equation. If you can just solve this quadratic equation, here we go. You could see that we have solved this particular quadratic equation to get the values of lambda. So because it is a quadratic equation, there should be 2 values of lambda, which means there are 2 magnification factors. We know what is a magnification factor. They are eigenvalues. So in our case, there are 2 eigenvalues. Great. We got the eigenvalues. We got the unknown. Next, we have to find out the eigenvectors. Because there are 2 eigenvalues, there should be one eigenvector for one eigenvalue, and there should be another eigenvector for the second eigenvalue. So there should be 2 eigenvectors, each corresponding to its own eigenvalue. So first we will take the first value of lambda, and then we will find its corresponding eigenvector. Then we will take the second value of lambda, and we will find the corresponding eigenvectors. These corresponding eigenvectors are called mode shapes. So here we go. In order to find the eigenvectors, so here we go. We will first take the first value of lambda. So lambda should be equal to 3. So that is the value that we are going to take first. And we don't know the vector. So here is the unknown vector that you could see that is the unknown vector. Now what I'm going to do is, you can take it is an unknown vector, but I know that it is any vector along its line of action. That's what we saw. Because when a vector is hit by a magic matrix, it can be any vector because it simply elongates and or diminishes. It can be any vector. So what I will do is I will simply take a vector along its line of action in such a fashion that its horizontal component is 1. Okay, there you could see that I have taken a vector Along its line of action, of course, I don't know what is the vector, but I can take any vector along its line of action. That concept we have already established. So what I'm going to do is I'm going to take the horizontal component of the vector to be 1. So I don't know obviously what is the vertical component because I don't know the vector. But I'm taking a vector where its horizontal component will be 1 and I don't know what is the vertical component. So I'm saying that the vertical component is b and the horizontal component is 1. So now I know what is the vector that I'm working with. I have taken a vector where its horizontal component is 1 and its vertical component is b. I can take that because I have taken this vector along its line of action. So there it enables me to give me this value, that is 1b. Of course, I don't know what is the values of what is the vector that I'm working with. Yes. And I do know the value of lambda, which is 3. So in the next step, I'm just going to substitute for lambda. I'm just going to substitute 3 and I'm going to take this 3 inside this matrix. So I'm getting this. Now, if you look at this equation, the only unknown in this equation is going to be b. So let me simplify, do the matrix multiplication. So you get this. So you can just multiply the first row with the column to get the value of b, or you can alternatively multiply the second row with the column and you can also get the value of b. In both the cases, you will end up with the same value of b. So I got the value of b, which means that in the original consideration, we took the horizontal component to be 1. Now I got the vertical component also. The vertical component is found to be 1 for this particular matrix. You can just work for any matrix, right? For this particular matrix, the vertical component is 1, which means that it just proves the fact that we discussed initially, that we started with the 1, 1 vector. So we end up with getting 1, 1 vector. So we are able to determine what is the eigenvalue, and we are also able to determine what is the corresponding eigenvector. So now we have to take the second value of lambda, which is 1. So here we go. This is the second value of lambda. That is lambda is equal to 1. We are going to do exactly the same mathematics and you can find out the value of b. Here is the value of b, that is -1, which means that that magic matrix is not only a magic matrix for the 1, 1 vector, it's also a magic matrix for 1, -1 vector. So these two vectors are the corresponding eigenvectors for that particular magic matrix. So one vector is 1, 1 vector, the other vector is 1, -1 vector. So these two vectors are the corresponding vectors for that magic matrix. So we are able to find the lambdas, two values of lambdas. In our case, one value of lambda is 3, the second value of lambda is 1. And we are also able to find the corresponding eigenvectors, 1i plus 1j, and we are also able to get 1i minus 1j. So yes, we are able to find the magnification factor eigenvalues and also the eigenvectors. These eigenvectors are called as mode shapes. Now, how is this concept going to be useful in failure theories? So we are going to see that in the next video. But I have to tell you that the concept of eigenvalues and eigenvectors are extensively used. They are used in vibration analysis and structural analysis. They are used in, say, for example, in the finite element formulation of the mass matrix. If you just come up with the concept of lumped mass matrix, then the vibration analysis problem just becomes an eigenvalue problem. And it is used by data scientists to represent data for data reduction and also to represent the data visually. It is used in Google. You know, the Google ranks the websites. It just uses the concept of eigenvalues and eigenvectors. Of course, in Schrodinger's equation, we are using eigenvalues and eigenvectors. So we can go on multiplying, giving illustrations about the amazing applications of eigenvalues and eigenvectors. So really cool concept used in machine learning, used by data scientists. And in the next video, we are going to see how in failure theories, in the context of failure theory, why these eigenvalues and eigenvectors are important, which means that the state of stress at a point can be represented as an eigenvalue problem. how. And that enables us to develop failure theories like von Mises failure theory, maximum distortion energy theory. We are going to delve deeper into the subject matter. Thank you all for your patience. Enough for today.